Hello, we're Team 2, Jongho Jung, Jungmin Lee, and Jaeyoung Jang for the TERM project in CS572 Intelligent Robotics. In this video, I will present TERM project progress. We choose the paper adversarial network because it presents a labor-free robot skill embedding learning framework. The learned embedding are transferable real-world robot tasks can be evaluated using synthetic and real-world datasets. And finally, the code and data sets are publicly available. For the summary of paper, we should introduce imitating learning. So what is imitating learning in nature? As you can see the baby, who learns some skills by imitating people in front of her on the video. Intelligent beings, including humans, tend to learn from imitation without extra supervision and can transfer the learned skill to an unseen environment. This is a natural instinct that saves a lot of time and effort. In addition, they can then easily learn novel tasks with their learned knowledge. However, most deep reinforcement learning methods typically learn solutions from scratch for every task and often rely on manual and do not transfer to new tasks in general because its policies and representations are task specified, which means that this approach is not only inefficient but also limits the versatility and adaptivity of the systems that can be built. In addition, in a typical robot learning task, each agent behavior is often treated as an discrete action. However, in reality, tasks and skills are continuously learned like humans. Therefore, the concept of continuum of skills was introduced. ASN introduced in select paper proposed an unsupervised skill learning framework from video inputs. The learned embedding from ASN can be then transferred to learning unseen skill by an RL agent. We conducted a paper survey in imitation learning for improvement plans. The same authors from ASN published this year a paper titled What Matters in Language Conditioned Robotics Imitation Learning over Unstructured Data. This paper deals with combining language guide to imitating learning to enable a robot to run perceptual and linguistic understanding together with task agnostic control in an end-to-end manner. Although this is a new imitation learning research, we thought that this was not adequate for implementation ourselves, since its paper requires additional natural language annotation on a frame-by-frame basis.
Here's examples of our dataset from the real-world block task dataset. So on the left, we see the stacking two blocks, and on the right is stacking color blocks. And third one is separating blocks, and fourth one is sorting blocks. So take this dataset, and we ran an experiment on these samples. And on the right, we see the progress of the experiment, and we can measure by these metrics that are plotted on the right. For example, for the alignment loss, we see that it decreases with step, and the distance between the positive and negative embeddings for the anchored embedding on the first graph is getting larger over time, and the entropy loss decreases in magnitude. So we can confirm that this experiment is going well. And given this, we visualize the embeddings over various steps, and over the steps we see that at the end at 90,000 steps we see the class features are much more discriminated from one another. But we also checked that the author provided pre-trained model it yields this embedding visualization, but you see that our experiment at 90,000 steps has more distinguishable class features than the pre-trained model. So we can confirm that our experiment went well.
Now I will introduce control policy experiment. To verify effectiveness of their embedding network, they conducted control fallacy learning experiments using pre-trained embedding networks. They used embedding network as a reward function of PPO algorithm. Note that to reproduce these works, we need the synthetic data sets and reinforcement learning experiment setup. Unfortunately, the author did not release the synthetic data sets and RL experiment setup. Therefore, we investigated the environments as similar as possible to the experiment conducted in this paper. We find similar setup so-called PandaGym. PandaGym is robotic arm simulation environment that is compatible with stable baseline 3. As you can see here, there are several different tasks. We select the stack, slide, pick and place, and push as a target task. In the right side of the slide, this is the reward function that will be used in PPO training. To this end, first we collect 5-view image to construct the training data sets. Since we need to train our embedding network, we collect a data set to train embedding networks. As you can see here, we collect image of each view in synchronized manner. This data set will be used for fine-tuning our ASN. Next, we try to implement reinforcement learning setup in PandaGym. However, there were some problems in this process. Since there was updated in Gymnasium current PandaGym, package is not compatible with reinforcement learning environment. So we are in the progress of debugging and attempting to downgrade the package to repair this part. We also try to use other RL environment setup, such as Pipeline. This environment also very similar to previous experiment setup. Now we are trying to fine-tune ASN network to extract better switcher representation. So currently we modified the code for fine-tuning with the collected synthetic data sets. These are our project timeline. We will improve ASN in learning more discriminative features. And second, we will do integration of the improved model to RL and test on RL tests. And third, verify our generalization capability of our models in its experiments. Thank you for listening our presentation.